In this section, we'll learn about sentence generation and text modeling using machine learning models. Machine learning can be used not only to predict and classify, but to generate sample data. This actually ends up being an interesting technique to generate testing data that has a statistically realistic feel, even though it's completely synthetic. State-of-the-art generation isn't quite good enough to write Shakespeare, but you can write text that statistically simulates Shakespeare, which is useful for, say, loading full-text indexes or getting a natural distribution of data in a database. So in this section, we're going to take a look at three topics: a name generator to generate city names, a sentence generator to generate text, and then we're going to learn what everyone wants to know: how to make a fortune with machine learning, which is to say, to make a clone of the classic program Fortune, which will generate a random saying with machine learning. Now in this video, we'll take a look at name generation and build a name generator workbook. We'll get the project source code, and then we'll look at character level encoding for these generation machine learning models. We'll build a character-based language model, and then we'll build up a recurrent neural network model that'll generate text using a recurrent neural network generator, and then finally we'll show some names that have been generated by this approach. Now all of the models in this section use recurrent neural networks, and they can be very slow on a CPU. In fact, you can get at least 20 times faster execution if you use a GPU, so I definitely recommend running these samples with a GPU, otherwise plan a lot of time for them to train. I'll go ahead and leave the link on the screen here to download the code that goes with this section of the video. We have several IPython notebooks inside this repository that we'll be using to work along with. Alright, now we can dive into the name generation IPython notebook that's in the source code that we've downloaded. At the beginning, we're going to be generating a language model, which is a way of representing text and strings, and we're going to focus on character-based language models and character-based encoding. We're going to use the base estimator and transformer, and again be building an encoder that extends the scikit-learn style interfaces. We're building a transformer that uses the base estimator and transformer mix-in that will transform text, a string, into numerical encoding. A couple of parameters passed to our constructor: the context length and the maximum ordinal. So the context length is going to be the number of characters that we pick out of a string that are then used to predict a subsequent character in our model. So for fitting, we don't really need to do anything because we are going to be using predefined ordinal indexes. We're going to use the ASCII integer representation of each character. So we can move right into transform, where we're going to be taking strings, which is going to be an iterable source of strings, and encoding this into a numerical representation that we'll be able to use for subsequent processing in machine learning. The main thing we're going to be doing is taking a string, like the string hello that I'm typing here, and we're going to turn it into a series of context and prediction pairs. So if you take hello and you split it out with a context length of 3, it's going to be HEL, and then L, and ELL, and then O. And so we'll be using the subsequent character as a prediction target for the previous characters in the string. Alright, so we're going to be having an input iterable of strings, and we're going to forgive if a single string was passed in and turn that into a list so we can iterate over each individual string. And then we're going to set up a context and a target array. So the contexts will have the priors and the targets will have the characters following after. Then we'll enumerate each string, strip it of spaces and send it to lowercase, and then pad it with spaces at the beginning so that it's the minimum length we need to set to our context length. This way we can deal with strings that are shorter if we happen to encounter one in our source file. And then we're going to terminate each string with a CHR0. This way we'll actually have a stop character. So as our neural network is running, if it predicts a 0, we know it in its mind has predicted an entire word. And then we're going to loop through each one of the sources and contexts and make a string and encode them as integers. So what are we really going to do? We're going to set up a NumPy array of zeros, and then we're going to fill in the ordinal value of the character. So this is the ASCII value of each individual character, which is going to serve as our encoding of the strings, and then we're going to head and return that X and that Y. Now we're going to take the encoding that we've created, which is going to be an integer representation of each character, and then vectorize it and turn it into machine learning style format with a dense encoding, and we're going to generate one hot encoding based on these character ordinals. We're going to start off in our initializer by setting up the context length and the maximum ordinal character, which is basically the maximum ASCII value or Unicode value that we're going to process, and then create our character encoder as a component of this vectorizer that we saw above. Again, there's nothing to do to fit because we have a predefined source. And In our transform, we're going to be creating one-hot encoding matrices. So the X, the inputs, are going to be the context strings one-hot encoded, and the Y, the outputs, are going to be the target characters one-hot encoded. So in our transform, the main body here, we create an X and Y array that are Booleans, and we iterate through each one of the sequence encoded characters. And we take that character value, and we set the ordinal at that character value to be 1. The rest are going to be zeros, and thus we end up with our one-hot encoding. And then finally an inverse transform, where we can take a matrix of one-hot encodings, take the argmax to then get the ordinal value of the 1, and then decode it and then join it out into a string. So we can flatten things back out into a string based on the characters we have. Now here we can go ahead and give it a run, take a look at this character model vectorizer. We'll open up the cities.txt file, which I'll show you here in a second, the data that we're working on, and then we'll vectorize it and fit it. The X's and the Y's are a bunch of one-hot arrays. So you can see the array below for the X, it's a matrix, so it has a bunch of false values because there really only be one true value per column. And then on the outputs, the array, again, there'll only be one true value. In this case, it's going to be 101 is the character that we're seeing here from the first array. And this is the encoding that we're going to be using. So we're going to be predicting from a one-hot encoding of characters as a context to a one-hot encoding of characters as a target. So the cities.txt data we're looking at is just a list of city names from the United States, one on each line. So this is a simple text file where we're going to be setting this up as our training data and generating a machine learning network that's going to attempt to generate and predict an interesting city name that isn't necessarily in the source file. So we're going to be making up synthetic city names. All right, and now we've got our data encoded, we're going to build a recurrent language model that will attempt to understand the structure of these strings, in this case city names, and be able to predict and generate new city names based on that. We're importing stuff from Keras, it's just a sequential model. And there's one trick here, the CUDNN-LSTM is a super accelerated version of the LSTM recurrent neural network. And if you have an NVIDIA GPU, I recommend you use it. So I set up a GPU optimized flag to pass to the constructor here. And it'll use this version, and it is way faster. It's 20 or 30 times faster in my testing. So our fit for the model we're doing, we send it in the strings, and we have the number of epochs, which is the iterations, and the batch size, the number we iterate on each time. And then if we're GPU optimized or not, we switch out what we're using for our recurrent neural network information. Then we transform the strings into the X's and the Y's. We build up a sequential model that's simply a recurrent neural network with normalization, followed by another recurrent neural network with normalization. So it's a deep network, 2 layers deep. And then a 2-layer deep, dense network that uses ReLU. And then we finally end in a 1-output softmax. So our classic categorization approach with Adam and categorical cross entropy to predict an output character. Now looking at the training in this model, we just go ahead and set it up, pass in the cities.txt reading each line from the file, and then showing you the output of the training loop here. You'll notice that it actually starts off and converges the loss relatively quickly. We go from a little over 2, and then it rolls down through each epoch to about 0.5, and then really flatlines. More data would definitely be helpful here, and more training iterations may work as well. So this model is not particularly accurate with that relatively high loss value, so we're going to see maybe a few little strange results, but if you can get a bigger set of data, that would be useful. All right. Now this particular neural network we're not going to be using to make predictions. We're going to be using it to make synthetic data, so we're going to create a generator. Now the generator is going to take the model that we just trained as input and store it as a variable on self, and then we're going to have a generate method which takes a seed, which can be really any random character or value, and a maximum length, which is going to be sort of a stop point so we could avoid looping forever. So we'll go through the range maximum length, and we'll vectorize that seed, the character value we passed in, and then we'll make a prediction. So we'll pass the seed into the model and we'll predict the next character. And then given that next character, we'll inverse transform it and then turn it into actual ASCII character text and append it along to our seed. So our seed keeps getting built up character by character each time we go through the loop, appending and predicting and appending and predicting. So taking the tail of the predicted array and then generating it as an output. So you can see what these outputs look like here. This is kind of it's almost like a strange autocomplete using machine learning to predict synthetic ideas. So you can type in new or SM and smooth and smeed and smanly, and you can see that it's generating words that actually look like words, giving little character snippets. So you can use this approach on essentially any kind of text data. Now it's not necessarily going to generate, quote, real outputs. but it's going to generate statistically realistic outputs, and these end up being really handy as a technique to generate a large amount of synthetic testing data that you can use in your database, say for unit testing or indexing. Okay, we've learned how to generate short strings from training data by modeling at the character level.